this course is on applications of topology to neural networks. Yeah, okay. So the focus of this course will be on a particular type of neural network called fully connected feed-forward neural networks with ReLU activation. If that doesn't mean anything to you yet, don't worry. That's what I'm going to explain. So this mini course consists of 4 lectures. So this first one is going to provide all the background that you need to know about neural networks. So this is neural networks from the point of view of a mathematician. And so this first lecture is not going to have as much topology in it. It's going to be mainly just introducing sort of the background of this area so that then in the later lectures, we can really start applying topological tools. I've broken the mini course into 4 sections. Some are shorter than others. So if I finish one section early, I may just start the next section. And finally, these slides are going to be available online in a Dropbox folder, which I sent to Jose Luis, and he's going to share with you. So don't feel that you have to write down every single word because you'll have access. And yeah, so feel free to ask questions as we go along. I'm happy to, answer any questions or address anything that comes up. Also, if you can't read my handwriting at any point, let me know. Okay, so we'll start on the first of our 4 topics, which is the background. Okay, so here's sort of like the intro to what this course is about. So neural networks have been extremely successful recently. So you've probably all experienced them in some way. So neural networks is what's responsible for things like ChatGPT and self-driving cars, image recognition, new ways to do protein folding, chemistry things. Like they're just sort of they're everywhere. And they're incredibly successful. But because applications have been growing so quickly, the theory has not really caught up. There's a big gap between what can happen, what we can do in applications, and the mathematical theory of it. And many questions about why these things work and how they work are still mysterious. So we, as topologists, have this really very powerful set of tools. And so the question is, how can we use topological tools to try to open up the black box and understand a little bit some of what's going on in neural networks? Okay. All right, so I will now get into defining what a neural network is, and I'll give you sort of the basic overview, and at the end, I'll talk about some of the broad questions that are open. And then in the later lectures, we will refine these questions. Okay, so the first question you might have is, what is a neural network? What does it have to do with artificial intelligence? So there's sort of a hierarchy. So artificial intelligence, or AI, is basically anything that requires intelligence, that would normally require human intelligence to do. And this includes both working with data as well as like symbolic things, like, for example, automated proof checking things or other like symbolic techniques. That fits in AI. So a subset of AI is machine learning, which I'll abbreviate ML. And so ML has to do with like learning from data. So you have a data set and you're looking for patterns and trying to make predictions and so on. Does not have any like symbolic stuff. So then neural networks, or deep learning, is a subset of machine learning. And deep learning is the name for the field where what you study is or use is neural networks. So deep learning is a particular collection of techniques in machine learning, and they use it uses parameterized classes of functions, and these functions are called neural networks. The reason it's called deep learning is that these functions that you use are compositions of many simple functions. So like a simple function followed by another simple function followed by another simple function. And so that's why it's called deep, because there's like, it's a deep composition of these very simple functions. So we're going to be focusing in on here, these deep learning techniques. Yes, okay. So here's an example of the supervised learning regime. You've probably all seen this before. So it's linear regression. Did I skip a slide? Yes. Okay. So supervised learning. This is what the deep learning techniques I'm going to talk about are. So supervised learning is basically about fitting curves to data. So the setup is you have a bunch of data points, a finite collection of data points. Each data point consists of a pair. There's an input xi and an output yi. I think of these inputs and outputs as living in a product space. X is in the input space, Y is in the output space. So finally, or not finally, but next, you have a class of functions, and it is a parameterized class of functions. So I'm going to use script F to denote the class of functions. So these are functions that I'm going to denote by F sub theta. Theta is my parameter, and it lives in some space, parameter space. I'm going to use omega for the parameter space. So each parameter, theta, gives you one of these functions that goes from whatever your input space is to whatever your output space is. And the goal of machine learning, deep learning, is to find the function f theta in your family that best fits your data. Basically, just you've got some collection of functions, find the one that best matches your data. So this is the supervised learning regime, because each of your inputs x comes with a label yi. So it's like you're teaching your algorithm what the correct outputs are, and so you're giving it a labeled set of data for what the correct answers are. Okay, now I can go on to my. Okay, I'm getting better. All right, so the simplest example of this maybe is linear regression. This is not deep learning, it is machine learning, because it's not a deep composition of functions. But I think this illustrates what's going on. So you have a collection of data, inputs and outputs. For this example, I'm thinking of my input space as R1 and my output space as also being R1. And then you have the collection of linear functions. So my class F consists of functions F, M, B. So M and B are the parameters. And when I pick an M and a B, that gives me the function that sends a point X to the function MX plus B. So just parameterized family of functions. In this case, my parameter space is R2, M and B. And your goal is to find the function in this class that best fits your data. So how do you define best fits your data? There's lots of choices. A natural one is using least squared error. So this is my error function, L, error or loss. So it goes from parameter space to the real numbers. And so what it does is it takes a parameter, M and B, and then you look at the function that corresponds to that M and B. And so you compute for each of your data points the difference between the correct label, the correct output, and what your function predicts. Square it and take the sum. So this is the L2 norm of the error function. But you could have picked some other way to measure the error. For example, You could have used the absolute value of the difference, or really any function you like. Squared error just has not lots of nice properties. Whatever function you use, in the context of machine learning, it's called a loss function. Okay. All right, so that's the general setup. Basically want to do that, but for more complicated families of functions. And so this brings us to deep learning. It's exactly this setup, but for specific types of parameterized functions, function families. All right, so now we are ready to define fully connected feed-forward neural networks, which is the class that I'm going to focus on. So this is basically the simplest type of neural network. It's commonly used. There are many different types of neural networks, but even the more complicated ones often contain sort of pieces that are of this type. So if you want to understand the mathematical theory, I think this is the right place to start, with the mathematically simple functions. Before I define this, I need to first define something called an activation function. An activation function is a function, which I'm going to denote by sigma, that goes from Rn to Rn, where n could be anything, and it is given by coordinate-wise application of some function that goes from R to R. So just to be clear, you have a function from R to R, and you just coordinate-wise means you just apply it to each coordinate separately. So these functions, activation functions, they're usually nonlinear, and the point of them is that when you're going to build a big composition of many functions, these activation functions introduce nonlinearity into your big composition. Okay, so that's an activation function. And now we can define. First, I have some examples of activation functions. So the first example is the class that we're going to focus on. It's called ReLU. ReLU stands for Rectified Linear Unit. It's a very fancy name. All it means is the function x goes to max of 0 and x. And so here's the graph of the function. I don't know why it's called that. It has roots in computer science, but that's what it is. So we just apply this function to all the different coordinates. There are other activation functions that people use. I've listed a few of them here. Where does it appear? Like, well, yeah, it's right. So they all have different properties, and which one should you use? Why should you use a different one? We're starting to get into some of the many questions. It's kind of jumping ahead a little bit, but we'll see later that when you're training your neural network, sometimes it's hard to train with this. And if you have a little bit of a slope, it means that neurons are more active. They're not stably inactivated, and so sometimes training goes better. Anyway, yeah. Right. Why would you define these? I don't know. But the thing that works and that's used a lot is this ReLU function. It's computationally easy to deal with, and it's very commonly used. Yeah. Any other questions before I go on? Yeah. Okay. There's many others that you could list. I just listed a few. Okay. We're now ready to define a neural network. So this whole page is the definition. It's kind of a long definition. So you start with a bunch of numbers, n0, n1, all the way up to nd, and then for some reason, which I'll explain, I'm drawing a vertical line, and then another number, nd plus 1. And these are going to be natural numbers, so positive integers. So we start with that, and you also start with an activation function, which acts coordinate-wise. For us, this is always going to be the ReLU function. All right, now we can define the class of fully connected feed-forward neural networks with architecture, that's this list of numbers, an activation function, whatever your function is that you've chosen. It is a parameterized class of functions, f, script f. Each function is specified by a parameter that lives in some parameter space. And the key thing that makes this deep learning is the restriction on what these functions can be. Each of these functions is a function from Rn0, so that's the first number in your list, which is called the architecture, and it's a function to the final number in this list. What kind of a function is it? It is built out of simple functions as follows. So your domain is Rn0. Eventually, you end up at Rnd+1. And these intermediate functions that you take the composition of all of them have a very specific form. Each one, so I'm calling them F1, F2, and so on, is a composition of an affine linear map and then your activation function. So each of these maps, A sub I, is just an affine linear map that goes from whatever the appropriate domain and codomain is. And then, because linear maps can't do that much, you need to introduce a little bit of nonlinearity. So the point is, these are like really, really simple. And you just combine together a lot of them. So in this case, our parameter space omega is R to the capital D, where D is just the total number of entries in all of the matrices. Right, so I said that these are affine linear maps, but I could think of an affine linear map as a matrix, and I just list all of the elements that are in all of the matrices as a vector, and that is your parameter theta. All right, so that's the definition of a fully connected feed-forward neural network with ReLU activation function. You might wonder, why are these called neural networks? So in your brain, you have neurons, and neurons, they get inputs from a lot of other neurons. And then once the sort of amount of input reaches a certain threshold, they like turn on or activate and pass on information to another neuron. So you can think of doing one coordinate of one of the A maps is like getting a bunch of inputs. And then once the input reaches a certain level, that's when the activation function like turns on. So it's modeled in some very abstract sense on neurons in biological networks. Any questions so far? Say that again? Yeah, I guess so. Similar to Turing machines? Yeah. Right, I mean, right, it's some abstract model of computation. Yeah. Was there another question? Yeah. Go ahead. Go. Okay, yeah. Please, go ahead. They can be whatever you want. And that's one of the questions, is what should they be? Yeah. Yes. Yeah, so a Hopfield network is, was sort of the precursor to this definition. Yeah. But yeah, it's coming from that school. Yeah. Okay. Oh, so I wanted to clarify what I meant by affine linear. So by an affine linear map from one space to another space, I just mean something that takes a vector and it has a bias vector. So if I list my vector here, if I put a 1 at the final coordinate, when I take the w's are the coefficients on the coordinates, but then I add a number b, and so that's what makes it affine linear instead of like purely linear. If you want, you can think of this as a matrix W and B. Typically in the machine learning community, the W part, these numbers are called weights, and the B part is called a bias. Okay, so there are many other types of neural networks. You can change exactly what the definition of one of those little maps is. I think I skipped a slide. Let me go back. Yeah. So I just copied the structure of our family of networks here. And I just wanted to tell you some terminology. So first, these little maps that make up the whole map are called layer maps. Each coordinate function of each of these maps is called a neuron. The number of layer maps is called the depth of the network. And again, deep learning means that the depth is, well, more than one. And these intermediate spaces, like Rn2, and so, or Rn1, that should start with Rn1, up to Rnd minus 1, these are called hidden layers because you don't actually see them in either the input or the output. The width of the network or of the architecture is just, it describes these numbers and the n's that are the dimensions of the intermediate spaces. Sometimes it's the max of n1 through nd, or sometimes it means max of n0 through nd plus 1, but just generally sort of how big are those intermediate spaces. Okay. In what I'm going to talk about, we're usually going to take the final space, the output, well, I guess call this a d plus 1, to just be one-dimensional. Also, I wanted to point out that on the very final map, the last one, there's no activation function. So there's activation functions on all the layers through until you get to the last one, which is just linear. Okay, so as I was saying, there are many other types of neural networks. I'm not really going to get into the different types of neural networks, but you just slightly tweak your definition of which family of maps you're working with. For the remainder of this mini course, whenever I talk about or say neural network, what I mean is one of these networks of the form we just talked about. In particular, the activation function will be the ReLU function. All right. So we're getting through the background. We've now defined what a neural network is. Now we'll talk about what it means to train a neural network. So basically it means finding the one that fits your data the best. So you've got your data, your sample data, that's inputs and outputs. You've chosen a family of functions. You've chosen a loss function, that's your error function, like least squared error or something. And training means find the parameter that minimizes the loss or error. So when I gave the example earlier of linear regression, that's something we can do explicitly. You've probably done it in a calculus class. You search for the critical points and then you try to minimize the function. You can do it using calculus. But for these classes of families that are used in modern machine learning, they're too complicated. You can't do it explicitly. So you need to do some algorithm to approximate the best solution. And that algorithm is usually some form of gradient descent. This picture, which I stole from the internet, it is not my picture, is meant to illustrate gradient descent. So here you have coordinates of your parameter theta. In this case, it's like a two-dimensional parameter space. And then you plot your error or loss function. And so the way gradient descent works is you just randomly start somewhere. I guess in this picture, you start at that parameter. And then you look around and you find the direction where the loss increases the fastest, and you take a step in that direction. And then you do it again. You look around, you say, which direction is the loss decreasing the fastest? And then you take a step. And you just keep going until the loss stops decreasing. There are many subtleties here about exactly how you do that, but that's generally the idea. Great. So this just summarizes what I just said. Gradient descent, the idea is you just initialize randomly somewhere, and then you inductively take a sequence of steps in the direction of the negative gradient of the loss function to get your next parameter. Remember from calculus, the gradient is the direction where the function increases the fastest. So the negative gradient is the direction where it increases or decreases the fastest. And you just keep going until you don't make any progress. All right, so there's a few variants of gradient descent. Yeah. Yes, so this is this L depends on your data D, and it depends on your function, your class of functions. Yeah, yes, you can write out, well, so exactly what your function is changes from place to place, but you can write it down as like an algebraic expression in terms of the parameters, and then you just take the derivative. Yeah. There are a few details. Well, there's many different versions of gradient descent, but some of them describe which of the data points you use. So the full batch gradient descent means that every time you take a step, you use all of your data points to figure out which direction to go. But if you have a large data set, that could be really computationally expensive. Yeah.
It's context of gradient descent.
So the data set is D, and so this loss function L is like, it's like least squared error using D as your data.
Each element compounds my input value or the weight of the.
So I guess, so I'd say that my loss function goes from my parameter space, I'm not sure if I'm answering your question, to R. And so what it does is it takes a parameter, and then that parameter gives you a function. So theta gives you the function f theta. And so then L of theta is the error on your data of the function f theta. Did I answer your question? Okay. So in this first one, when you calculate the error, you use all of the data. So like L of theta is like the sum over all of your data points of the correct answer minus what your function gives you at that input, and we'll square it. The other variants are that when you don't use all of your data, mini batch gradient descent is that instead of using all of your data, I'll call it maybe batch, is you partition your data D into subsets of some fixed size, and you only use one subset at a time. So maybe if data equals, I don't know, data 1 union, data 2 union, so on, and each DI has size M, it's like then you use only the points in that batch. I won't write it out, but I'll say use points in that batch. And again, then you compute which direction is the best, and you take a step. And stochastic gradient descent is the special case where you only use a single point. You might think, why would this work? But they all work in different ways and have different sort of advantages, and there's trade-offs. Okay. So the geometry of this loss function, L, whatever it is, in particular, the level sets is called the loss landscape. So that picture I showed before, that is called the loss landscape. And so when you do this process of using gradient descent, stepping through parameter space, the thing you end up at is called the trained model. So it's your approximation of the best function. Okay. So next sort of little topic in the background of neural networks is generalization and overfitting or underfitting. So if you're a practitioner, you have your data, you pick your family of functions, you go through this whole process, and you find a trained model. The hope is that then when you give it like a new data point that it hasn't used in training, that it will output something useful. So that's called generalization. The idea that it describes how well your trained model does when you give it new data points. Underfitting is the situation where your family of functions is not complex enough. It's just the functions aren't flexible enough to represent your data. Well, represent it to the degree of, approximation that you want. Then overfitting is the opposite. It's that your family of functions is too complex, too flexible. And so you'll be able to find a function that has a really low loss or error on the data that you use to train it, but performs poorly when you give it new data points. Here's my my cartoon illustrating what overfitting is. The example is maybe you're using polynomials of degree 1,000,000 to fit a set of 5 data points. And here's my 5 data points. Like, you're going to be able to find one, but it's going to do crazy things away from the data. And so it's like not going to be useful. Okay. And okay, knocking out topics. Next, we're on topic 6. I wanted to mention 2 different approximation theorems. So the first theorem is called the universal approximation theorem, and it tells you that this class of functions can do a lot. That is, if you pick any compact subset of your domain and any continuous function on that compact subset, you can approximate it arbitrarily well using one of these functions. I should say approximate. What do I mean? I mean in the soup norm or the uniform norm. And when I say one of these functions, this is fully connected feed-forward ReLU neural networks with sufficiently complex architecture. So those intermediate spaces, they might need to be really big. You might need to have a lot of them, but if you use a complicated enough structure, you'll be able to approximate anything. In fact, you can show that you actually only need one hidden layer, as long as you make that layer really, really wide. Yeah. Mm-hmm. Mm-hmm. Yes. I think this holds for any activation function that is not a polynomial, which is weird. Yeah. There's various forms of this theorem that have been proven by different people. I guess two names that I thought I should cite are Cybenko and Hornick. I think Cybenko did, I forget who exactly did what. One of them did ReLU activations. Other people did other types of activations. It's been proven a number of times in different contexts. Okay, so that's saying you can do essentially anything, using approximations. The second theorem I wanted to mention, which is due to Aurora, says that the class of functions that you can get in this way, using fully connected feed-forward ReLU neural networks, is just all piecewise linear functions. So really what we're going to be talking about as we go forward is piecewise linear geometry and topology. Okay. Okay, so that is actually the end of my crash course on the theory of neural networks. That's like the background information. I know we haven't seen much topology yet. I promise it's coming. But now that I've sort of given you the big idea, I wanted to just sort of highlight some of the broad questions, which actually many of you in the audience have already been sort of bringing up. So these are very broad, and we're gonna make these questions more refined in the later lectures. But the first question, which I think you asked, is which architectures are you allowed to use, and which ones should you use? So, I mean, if you're a person who's actually trying to do this in practice, and you sit down and you have a data set, how do you pick which family of functions to use? Currently, there's not much theoretical guidance. My understanding from those people who do it professionally is that it's kind of an art. Over time, you kind of get an intuition about what types of architectures are likely to work better. But I think there's a lot of opportunity here for the theory to start to build up the theory to try to answer this question. Okay, so that's one kind of like big question. Another question is, why does overparameterization work? So I haven't really talked about this yet, but overparameterization is the setting where the number of parameters is way bigger than the number of data points. It's like that scenario I gave where you're using polynomials of degree 1,000,000 and you have 5 data points. So our intuition from families that are like polynomials is that this should not work, right? But it turns out in this context, it does work. In fact, this setting, the over-parameterized setting, where you have way more parameters than data points, is what seems to work the best in applications. And it is not fully understood why. So that's a question. Can we like rigorously theoretically explain why it works? Okay, so another question, again, these are like very broad, but is the question of interpretability. So say you've gone through this whole process, you had a data set, you trained a model, you got your function, and now you apply it to some data point and it gives you an answer. You might want to know, like, why did it give you that answer? Like what characteristics of the inputs made it give you that output? I mean, you can imagine, like, say you're using this to, like, maybe you're looking at x-rays of like, and you're looking for cancer and like scans of like images of x-rays, and your neural network outputs like, yes, with 99% probability there's cancer. You want to be able to say, this is why, like this is what it was looking at. So basically questions about like, can we understand why a trained model gives the output that it does, is another area that I think there's lots of rich questions in. And kind of related to that is my final question here, which is, which parameters or functions is gradient descent, whatever form of it you are using, likely to select? So I think sort of there's a consensus that the kind of the reason over parameterization should work is that somehow gradient descent is more likely to pick out like simple functions. But this has not been fully like established in a rigorous theorem proof sort of way. Okay, so that's the end of my first lecture. I think I still have 15 minutes. I will go on and start the next one. I knew this one was going to be a little bit shorter. But so the purpose of this was just to kind of introduce the area and sort of give you a sense of like what the questions are. So yeah.
I'm understanding that this scenario of work,
Yep.
so there are people that maybe work with trigonometric functions.
With trigonometric functions? Yeah, maybe. I don't know. Yeah.
Okay. You can go deeper in each of these subjects.
Yep. Yeah. 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 Mm-hmm.
First, these things, how long can they be? Or how long they are?
It depends on how complicated the task is. It kind of goes back to that question of what is the right architecture. So for if you want to do linear regression, you could just use one. If you want to have a very complicated function, it would be longer. It really depends. Yeah.
The second one is, we will study from the political view. Are there any other branches of mathematics that are studying this?
It's a great question. So, okay, so the question is, are there other branches of mathematics that are addressing this? Yes. So my feeling is that right now, the sort of theoretical side of deep learning is still in the very early childhood. At this point, there's tons of questions, and there's lots of people from lots of different areas who are trying to address these questions using different tools. So really, I think the answer to your question is, if you're a mathematician, whatever kind of background you have, there's probably a way to take that area of math and apply it to these questions in some ways. And there's lots of people doing that. And this is just sort of the angle that I am approaching it from, the topology geometry. Yep. Okay. Other questions before I? Yeah. Yeah. These two questions? No. In the theorems. Oh, yeah. These two theorems, yeah.
The last theorem said that the functions that we can obtain with this procedure are linear
piecewise linear, yeah.
These sigma functions that we mentioned in the definition.
Yes. I'm only going to use the ReLU function, but yeah. So I'm only.
But this sigma changes the following function.
Mm-hmm. Yeah, and you can choose which one you want to use. I'm only going to talk about the this one. And so this so this theorem is specifically about neural networks using this one. Yeah. There are other versions of this theorem for other activation functions.
I also believe there is for other fields, not only for R.
Mm-hmm.
It's in general the K field that solves some nice unique properties.
Thanks.
Any other questions?
Yeah. Yeah. Oh, the questions. The questions. These questions.
But I don't know if it can be classified as part of the big or it could be identified.
Sure. Okay. Yeah.
What is the neural network learning?
What is the? Say it again.
What is the neural network learning?
Oh, what is it? Great question. Okay, I'll add. Yeah. What?
No, why?
Yeah. Yeah, great question. Thanks. Okay, why don't we switch to my next one, if you don't mind. Great. Okay. So I'm now going to focus in on neural networks that use this ReLU activation function. So everything from here on is using this. Okay. So also, this one's longer. I'll talk for a few minutes and then I'll stop. Okay, so in this second category, which I'm calling polyhedral complexes and transversality for ReLU neural networks, these are sort of the 5 topics I'm going to talk about. So first, we'll start by just exploring some of the piecewise linear geometry of one of these functions. And I'll introduce the others later, probably after the break. Okay, thanks. So we're going to begin to explore and get a feel for what these things are. So we'll start with just a single layer, so just one of the simple functions. And in this example, we're going to have R2 as our domain and R3 as the codomain. So for this R2 to R3, our function will look like this. It'll take xy in R2, and it will send it to something that looks like this. So you've weight 1 times x plus weight 1, 2 times y plus a bias, and then you take the activation function, which is going to be this. And then you do this in each of the 3 coordinates. Okay. So how can we understand this? So let's look at, say, the first coordinate, I guess, or the jth coordinate. So the part inside is just an affine function. And remember, this function, sigma, is the one that makes negative numbers 0 and is the identity. So here's my little picture. So if you look at where this function becomes 0, so that's like this equation, this is the equation for a hyperplane, right? So maybe here's my hyperplane. And what the ReLU function does is on the side of the hyperplane where it's negative, it just makes it 0. And then level sets are parallel hyperplanes. So each coordinate function gives you a hyperplane. That hyperplane comes with an orientation. I think of the orientation as pointing into the side where it's positive. Okay. So here I've just drawn one hyperplane, but since there's 3 coordinates, I could draw 3 hyperplanes that all have their own orientations. So here I did that. So here's my R2. Let's just imagine that the 3 co-oriented hyperplanes look like this. So this is sort of the generic arrangement of 3 hyperplanes. And I've drawn arrows to indicate which side is the positive side. So H1 is going to be the hyperplane for the first coordinate, H2, the hyperplane for the second, and H3 for the third. So this obviously cuts our domain into a bunch of pieces. And what I wanted to do is visualize how this map works. So here's R3. Let's look at, say, this central triangle, which is sort of purple or gray. So here, none of the hyperplanes are active because they all are positive on the side that does not contain this. So this whole central triangle will be sent to the origin. I don't know if you can see it. There's a little purple dot there. Let's look at, for example, this yellow region. So if we look at our first hyperplane, H1, it's on the positive side. Wait, let's should say X is positive. I think I messed up my indexes. Okay, X. Yeah, if this is my first one, X should be positive. Yeah, sorry, my indexes are off. Here, X should be positive, and Y and Z should be 0 because it's on the negative side of the two hyperplanes corresponding to Y and Z. So it's going to become a one-dimensional line. If we take, say, this pink region, in the pink region, it looks like it's on the positive side of the third hyperplane and the positive side of the first hyperplane. So here, X should be positive, Z should be positive, but Y should be 0. So that means it will become a two-dimensional object in the ZY plane. And you can do the same thing for each of these other pieces. In general, you can see that these things where two coordinates are positive become a two-dimensional thing. Spaces where one coordinate is positive becomes like a one-dimensional simplex. So what we can see is that what this layer map is doing is that it sort of like folds up the domain. And it sends it into the all positive orthant of R3. And it's linear except on these hyperplanes. So it's piecewise linear, and its nonlinear locus is the union of these three hyperplanes. So it's linear on regions of R2. Take away that. Yeah, okay, let's do another experiment. Let's see what happens if we put different orientations on the hyperplanes. So I have the same three hyperplanes, H1, H2, and H3, but instead of writing X positive, Y 0 thing, I'm just going to record the signs with respect to the three hyperplanes. So in this case, I've oriented so that they're all pointing into this middle region. So this is where they're positive. So if we look at, say, the yellow region, it's on the negative side of the hyperplane that corresponds to the first coordinate. So I put a negative, but it's on the positive side of the other two hyperplanes. So I put 2 pluses. We can do this for each of the regions. Like the central region, all three, is in the positive half space for all three hyperplanes. So it's plus, plus, plus. And so, kind of going around, you can assign this coding to each of the hyperplanes, or each of the regions. And then these codings tell you essentially what the dimension of the image will be. So like this yellow one has 2 pluses, meaning like 2 of the coordinates are not 0. And so it becomes a two-dimensional face. It lives in a space where two coordinates are positive. The purple one, all 3 are positive, meaning that it just acts as a homeomorphism. And so this purple one just becomes a triangle. And so you can see it just kind of takes it and like folds it up. So these signs, I call them the sign sequence. So, and it's just convenient to record this for each region. So it's an assignment of either plus, minus, or 0 if it's like on the hyperplane to each region for each coordinate. let's see. Yeah. So I'll finish in a moment. But so far we've been thinking about just a single layer map. But of course, in these families that we're talking about, we're going to compose a bunch of these functions together. So let's just try adding one more layer. We're going to do it in the simplest way possible. So we have our R2 to R3, but we're going to add one more layer to R1. So let's just like think about what this does. So our first layer, it takes R2 and it sends it into R3, and it's the positive in the positive orthant of R3. So now let's think about this next layer. So this layer, so it has a form that looks like this. And so we can play the same game. This determines a hyperplane in R3. So that's what this red object is meant to be. This is where this expression equals 0. And then again, you apply sigma to it. So on one side, it's positive. On one side, it's negative. So, yeah, so I tried to draw, I tried to draw that. Yeah, okay. Now, so where is the whole thing linear? So it was linear on our original hyperplanes, but now if we look at the intersection of this hyperplane with the image, and then we pull it back to the original domain, you can see this sort of like triangle shape here is meant to be the intersection. When you pull it back, its pre-image is this shape. So now we have more regions, and the total map is linear on R2, take away the hyperplanes from our first layer, as well as the pre-image of the hyperplanes from the next layer. These ones are often called bent hyperplanes because you start with a hyperplane, but when you take the pre-image, they bend. Okay, I think I should stop there, and I'll continue this in the next lecture. Thanks.